Okay, class, today we are talking about multiple quantifiers. So this just means we're going to string together there exists and for all, and do a couple of them at a time instead of one at a time. So it's nothing really new, just new ways to do things we already know about. Okay, so consider the statement. So how about this? For any x and y in the integers, x plus y equals 0. So by now, I hope you can start to recognize just by reading things when they're true or false. So this is a false statement, but that's okay. What we want to do for now is really just think about what it really is, which is it's a statement involving two quantifiers, but one of them is like secretly hidden. And really, it's got to have two quantifiers because it has two variables in the predicate. So this is something of the form p of x comma y. It's a statement which is true or false depending on two variables. So it's got to have two quantifiers, but I only wrote one. And that's just because sometimes we do things like that. But really, we could think about it in a different way, which is something like this. For any x in the integers, and then I'm going to use parentheses just to separate the quantified things. So this is really saying for any x in the integers and for any y in the integers, p of x comma y. So I'll write that in parentheses too, even though we don't need to. Sorry, that looks like a weird parentheses. How about like that? There we go. So we can think about it as a statement with two quantifiers. And it's two universal quantifiers. And it's false because what it's saying is that p of x comma y has to work for any x and for any y, not just for any of one kind, and then the other one could be whatever you want. No, it has to be for any of both. So for example, if x equals 3 and y equals 5, then that's an x, which it doesn't work for, and a y, which it doesn't work for together, because I get 8 equals 0, which is false. Okay, so when you have two for alls together, it's hopefully not so bad. It just means for all of one and then for all of the other. You can even think about it as something like this, which is going to come in handy later. You can think about it as a for all x statement. And then you could think about this entire second part as a predicate involving x and y. So this is a legitimate way to think about this, and it is what we'll be doing later. So now p of x comma y is different. Over here, it was just the last part, it was just that x plus y equals 0. But now the predicate is for any y in the integers, p of x comma y equals 0. Or sorry, p of x comma y, which is that x plus y equals 0. Okay, so we'll more on that later. Let's do some more other types of examples for now. So now let's think about mixing up some quantifiers that are different. So for any x in the integers, there exists a y in the integers. So remember, there exists always comes with a such that. And again, I'm going to do parentheses just to keep things together. Such that, and then our predicate is going to involve x and y. Well, we're just going to use the same predicate. Okay, So here's another statement involving two quantifiers, but now it's a for all, and then it's there exists. So what is it really saying? It's saying that no matter what x you start with, if we break this down, start with any x in the integers, then there's gonna exist a y making the next thing happen, which is that this equation will be equal to 0. So that's how you read a for all there exists. No matter what you start with, there will be a y making x plus y equals 0. So this one is true. So for example, this doesn't prove it's true because it's just an example. If x equals 5, then does there exist a y that makes x plus y equals 0? Yes. Then y equals -5 makes x plus y be 0, because you get 5 plus -5 equals 0. And so this statement is saying that this will always work no matter what x you start with. And it will. So if I start with 6, then I'll just use y equals -6. That also exists in the integers. Same idea. So in general, why is it true? It's true because for any x in the integers that you start with, then -x will be the y that you need. And that'll always be in the integers. And so it exists in the integers. And when I add it together with x, I do get 0. So the claim, when you say for all first, is that no matter what you start with, you'll be able to find something that makes the predicate be true. So notice the difference between that one and the next one. It's very subtle. Subtle difference between that one and the following one. So all I'm going to do is rearrange it. I'm going to put the there exists first. So there exists an x in the integers such that, oops, sorry, such that comes before the comma, such that, oh wait, no it doesn't, such that for any y that I have in the integers, x plus y will be 0. So I kept the predicate the same at the end, but I've rearranged my there exists in my for all. So what is this saying? This is now saying that there's like some super special integer that it exists, and it has this amazing property that no matter what other integer you have, if you add it to this super special one, you'll end up with 0. And this is false. There's no number like that. No integer x has this property. Now, showing something does not exist is kind of hard. So for example, I can say why specific things don't work. So for example, x equals 5 doesn't work because 5 plus every single number that I can think of is not going to give me 0. For example, if I use 1, I don't get 0. But it also doesn't work for plenty of other numbers. It only works once. But that doesn't matter because the claim is that there exists a number which, when you add it to any other number, y, you'll get 0. But that's not what's happening here. If I add it to 1, it doesn't be 0. If I add it to 2, same thing. Only once does it work. But this is not really a proof that no such number exists. How do you know I haven't looked hard enough? well, we haven't learned enough proof techniques to actually prove this one in a very nice way, so I'm not going to do it. But I hope you can convince yourself that it's false. There's no number that exists which, when you add something to it, it'll always be 0. If I change add to multiplication, this will actually be true. So I'll let you think about that. Okay, so now that's when I do there exists for all. So the idea there is that what you're doing is you're claiming that something is super special and that it works no matter what other number you use, that the predicate will happen. That's the general idea. Okay, so what about 2 there exists? There exists an x in the integers such that there exists a y in the integers such that x plus y equals 0. So when you write them separately, it sort of sounds a bit weird. But what you're really just saying is that there's some special number, x, such that there's another special number that when you add it to x, you get 0. And it's true, but that number is not even that special. There's lots of numbers that this works for. So remember, there exists only has to work for one. You just have to find one integer satisfying this thing. But many integers do. In fact, all of them do. So for example, this is true because 3 is in the integers. And -3 exists in the integers as well. And when I add them together, I do get 0. So it works every time, but it only has to work once for this to be true. So you could have said the same thing. You could have used 6 with -6, or 10, -10, or -100 with 100. Doesn't matter, as long as they're integers. Any of them give you an example, and in this situation, an example is enough to prove that it's true, because all you're trying to say is that there exists an x in the integers such that there exists a y in the integers such that x plus y equals 0. Typically, when you have 2 there exists, you really just say like this. You really just say there exists an x and a y in the integers. As long as you're claiming they're both from the same place, in this case the integers, then you could just put them together like that. And it's the same thing. Okay. So when you have 2 there exists, the general idea is you're finding a pair satisfying the predicate. You're just finding a single pair. If you can find a single pair that satisfies the predicate, that's enough for the whole thing to be true. Okay, so those are the 4 possible ways to combine for all there exists with each other. And you might be able to imagine how you could have even more. You just sort of follow the same rules. Okay, but next what we want to move on to is negating multiple quantifiers. And it's just going to come from previous rules. It's not going to be something too new. So the way it works is you just use the rules we established last time. So let me remind you of those. If you negate a for all x in something, then that just becomes a there exists an x in that something such that the predicate does not happen. And vice versa. If you negate a there exists, then it becomes a for all, and then negate the predicate. Okay, so that's a mini thing from last time. So we're just going to use this multiple times to see how it works when you have multiple quantifiers. So here's an example. We'll just use the same stuff we've been working with. So let's try to negate this thing that we looked at. There exists an x in the integers such that for any y in the integers, x plus y equals 0. So real quick, was this guy true or false without the negation? This was false, right? There definitely is no number such that if you add it to any other number, you get 0. That's not true. So the negation better be true. And that's one way to check that we've done it correctly. So the negation should be true. Okay, so the way we're going to figure it out is by realizing that we can rewrite this in a way that I hinted at before, which is we can think of this as there exists an x in the integers such that, and then both of these pieces we could think about as a single p of x comma y. So we're just saying the same thing in a more compact way. We're still saying the same statement that there exists an x in the integers such that something happens. That something is dependent on x and y, and it changes depending on x. So we can call this a predicate. We can write it like that. Then we can use our rule up here. How do we negate a there exists? Well, it just becomes for all. So for any x in the integers, and then you negate the predicate. And then we remember, oh, that predicate is actually 2 pieces. So now I'll use that. So for any x in the integers, and then a pattern will be established. Negate, what was that? What was it for all y in the integers, p of x comma y, where this p of x comma y is different. It's just x plus y equals 0. So I probably shouldn't call it the same thing. Let me not do that. Let me just call it x plus y equals 0. And now this is just a negation of a for all, which that's what this rule is for. We already have that rule. So if I negate a for all, it becomes a there exists. And then this guy gets negated. So what's the negation of x plus y equaling 0? That's just that x plus y doesn't equal 0. So I'm not going to rewrite the whole thing. Let me just say that x plus y does not equal 0. Okay, so here's the complete negated statement. So let's just read it back to ourselves to think about how it's the same. So originally, the statement was that there does exist an integer such that for any other integer you pick, x plus y equals 0. So the negation should be that it is not the case that there is an integer such that no matter what integer you pick, when you add them up, you get 0. So if you're saying that such an x does not exist, then you're saying that no matter what x you start with, you will not be able to say the rest of it. You will not be able to say that for any y in the integers, x plus y will be 0. And that's what this is saying. And if you're saying that you won't be able to have for any y in the integers x plus y equals 0, what you're saying is that there's got to be some y, that's what this is saying, such that x plus y won't be 0. And that's what this is saying. Okay, so read it back to yourself a couple different times and try to convince yourself of it. But the general rule is that the negation flips each quantifier and then negates the final predicate. So I can write down another little example here. We can do it using this idea. So if I say the negation of, for any x in the integers, I'll just keep doing the integers, but it doesn't have to be that. For any y in the integers, I'm going to add a third one. There exists a z in the integers such that x squared plus y squared equals z squared. Okay, so I'm just writing parentheses to separate it, but you don't have to do that. Okay, so what is this saying? This is saying, so ignore the negation for now. This is saying that no matter what x you pick, and no matter what y you pick, sorry, this should be a y, the second one. No matter what two numbers you start with, if they're integers, you'll be able to find a third integer satisfying this equation. So I believe this is false because I know the Pythagorean theorem and I know about Pythagorean triples. So for example, if x is 1 and y is 1, there does not exist a z satisfying this because the left side is just 2. There's no integer which when you square it gives 2. The actual answer would be square root of 2, which is not an integer. So I know this is false already, so the negation must be true. And now let's try to negate it using our quick rule. So the negation should pass through all of the quantifiers and flip them. There is going to be an x in the integers such that there's also going to be a y in the integers, aka there's going to be a pair of numbers. There exist two numbers such that whatever number you decide, no matter what it is, whatever third number you pick, the predicate will not hold, meaning that x squared plus y squared will not be z squared. And that is exactly what we've proven just in a little mini proof right here. There does exist an x and y, so I could pick 1 and 1, but you could pick up something else, so it'll still work. There do exist two numbers such that no matter what z you use from the integers, you're going to get that x squared plus y squared does not equal z squared. And that's true because the only way it would work is if it was square root of 2, but that's on the integers. Okay, so that's going to be it for today, and I will see you next time.